Okay, question number 3. We are still in section 1.5, the last section of chapter 1. This question is actually in the book. It's exercise 4 in the book. It is not in your assignment, but you'll see this question in the book. See the pattern below. Here's a pattern, okay? 1 is 1. 1 plus 3 is, I didn't have that. It's 4, which is 2 squared. 1 plus 3 plus 5 is 9, which is 3 squared. Squared means, 3 times 3. 1 plus 3 plus 5 plus 7 is 16, which happens to be 4 times 4, which is 4 squared. 1, 3, 5, 7, 9 adds up to 25, which is 5 times 5, which is 5 squared. It seems like when you add these numbers and you have to describe in your own language what you're adding on the left-hand side, it turns out the sum seems to be always a squared number, which means it's some integer squared. It's a number multiplied by itself. Okay, now this is a pattern. Is this pattern going to continue? If so, try to describe what that pattern is in precise language. That is called a theorem in mathematics, something that is proved to be true, but you have to specifically and precisely write that statement in English or in whatever the language you use. If it is wrong, maybe this pattern does not continue forever. Then you have to find what is called a counterexample. What happens if, and by the way, do you know if this will continue forever? That would require a mathematical proof, right? Unless you find a counterexample, then you can prove that this does not continue. So there's all kinds of interesting stuff going on here, right? Let's try to say what we want to say, right? Do you see the pattern of the left-hand side and the pattern on the right-hand side? Can you make a conjecture? Conjecture is a guess. Conjecture is a mathematical statement which you think is true, even though you can't prove it, and that would be called a conjecture. And once a proof is given, that conjecture becomes a theorem. All right. So a conjecture is your guess, your hypothesis. Okay, and if you have a proof, a mathematical proof, this becomes a theorem, a statement that is proved to be true. Once a proof is given and the theorem is proved, then that theorem stays true forever. Okay, that is a powerful statement in mathematics, because once a proof is given, the theorem is going to be true regardless of what theory may come in the future. The theorem will still be true. So for instance, the Pythagorean theorem is one of the most well-known theorems in mathematics. It'll never be proved false. Okay, it's always going to be true with the assumptions of what we call geometry. So, all right, so try to make your statements as precise as possible. And is this true? Can you prove it? Right. So the conjecture, let's try to write down what we are observing here. On the left-hand side, you have numbers like 1, 1, 3, 1, 3, 5, 1, 3, 5, 7, 1, 3, 5. So here, the last ones, you have 5 what? 5 numbers. 5 what kind of numbers? 5 odd numbers, right? Positive odd numbers, starting at 1, right? So the left-hand side can be written as the sum or the the answer to addition of what? Of the first, not just first numbers, first odd, well, first, I'm going to leave a little space here because I'm going to fill in the space in just a few seconds. The sum of the first blank positive, because these are not negative integers, like positive integers. Integers are these whole numbers. Positive integers are the whole numbers. The sum of the first, well, 5 odd numbers is 5 squared. The sum of the first 4 odd integers is 4 squares. Sum of the first 3 odd integers is 3 squared. So the sum, in a general statement, the sum of the first n positive odd integers is n squared. You see that? If n is 5, that would apply to this statement. The sum of the first 5 positive odd integers is 5 squared, right? So this is a precise way of writing what we are observing. Sometimes this is the hard part of stating, something related to mathematics. Like, what are you trying to say? Like, can you say what you want to say in a precise and concise statement? Okay, simple but precise statement. And this is precisely what we are observing. The sum of the first n positive odd integers is equal to n squared. So if this argument, or if this hypothesis or conjecture is true, this is the conjecture. If this conjecture is true, then the next one, the sum of the first 6 positive integers, odd integers, is going to be 6 squared. The sum of the first 12 positive odd integers should be 12 squared. Is that right? Well, let's try the next one. 1 plus 5, and it's okay, by the way, to explore. This part is called exploration, because all you're doing is to just, consider a few more examples to see if this pattern continues. That's the first. Is this the first 6 odd integers? 1, 2, 3, 4, 5, 6, right? So we know what happens to the first 5. First 5 add up to 25. So add 11 to it, and that's what? 36. Ooh, that is 6 squared. How about if you have 7? First 7 odd integers, you have to have 13 in there. Of course, the first 6 of them add up to 36. So add 13 to it, that's 49. Ooh, that's 7 squared. That looks too good to be true, right? I mean, this can't just be accidental. Can you prove this for all n? Ooh, that's a tall order. You have to prove it for every single n, and of course that does require some advanced mathematics, which you don't have to worry about for this class. Okay, but I want you to be able to state what you're observing in precise language. That's what we're doing. Now, for this problem, if you're wondering if there's a good way to understand this, maybe not a concise or precise proof, but maybe there's a way to understand this. There is a simple way to understand this. Okay, I'm going to use a different color to say that, okay, 1 is equal to 1. That's easy, right? That's 1. Now, when you have 1 plus 3 equal to 4, what you can do is to draw a 2 by 2 square, or actually the 2 by 2 points. That's 4, right? The next one is 9. So let's do a 3 by 3, and that's 9. 4 by 4 is 16. So 4 times 4, I make 16 dots, or 16 points. 4 by 4, and then 5 by 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Go ahead and do this on your notes. Nothing like hands-on. See, sometimes you can watch me do all these problems as an observer or as a spectator, but you will never learn as much as if you actually draw and think for yourself, because there is something that connects your hands with your eyes and with your brains, and you will learn much better if you do this on your own. Okay, so the first one is just 1. Okay? This is just 1. The next one, this, if you think of this as the front, and if you have a back, maybe you can think of this, this thing as a pitcher, and you have the first and second and third baseman. Sorry, no shortstop. That's 1 plus 3. So you see, you have 1 in the first layer or first row and 3 in the second row. That's 4. Interesting. All right, same thing. 1, this is the first row, and then you have 3 in the second row, and you have 1, 2, 3, 4, 5 in the third row. That's 1 plus 3 plus 5. And that's 3 squared, because I drew 3 times 3 at the beginning, right? How about 4 by 4? Do the same trick. This is like the front of the theater. You have the first row, second row with 3 seats, third row with 5 seats, and then the next row has 1, 2, 3, 4, 5, 6, 7. and 1 plus 3 plus 5 plus 7, the sum of the first 4 positive odd integers is 16 because I drew 16. So the point is, every time you go to the next row in this theater, you're adding 2 points, right? One on both ends of this, and therefore you would be adding that next odd number, and that seems to be the reason why this conjecture is true. Okay, try with 5 rows. 1, 3, 5, 7, and 9. And if you add these, you get 25. So this is called sometimes called quote unquote proof by picture, or proof without words. Okay, you see that this is a proof by picture, and this picture proofs. Okay, there is a way to prove this conjecture mathematically. This actually is a true pattern that would continue forever, no matter what this n is. Okay, so for instance, I know, and you know, because this conjecture is true, that the sum of the first 3,000 positive odd integers is going to be 3,000 squared, 3,000 times 3,000. Okay, but the proof is more complicated than what we want to do for this class. But I do want you to think of this example as a great illustration of recognizing patterns and writing down precisely what you mean by what you're guessing, the conjecture, right? And sometimes pictures can give you a great insight into solving a problem. Okay, going along, number 4. Count the vertices, edges, faces of a tetrahedron, a cube, and a dodecahedron. I know these words may not be familiar to you. You know what a cube is. What pattern do you see? Try a soccer ball if you wish. So you can take a look at this. I'm going to do just the soccer ball is very hard to do. Dodecahedron is hard enough. Tetrahedron, if you are a tea enthusiast, you know that some fancy tea bags come in tetrahedral shape. It looks like this. Okay, so it's like a pyramid, except the pyramid has a square base. This one has a triangular base. So this is a solid surface, basically, where you have 4 sides or 4 faces, and every face is a triangle. Okay, in fact, an equilateral triangle if it's a regular tetrahedron. Okay. So here I should have drawn this. I'm going to do this on my. Can I do this? Yeah, I can do this. I can move this ahead. Right, great. All right, let's talk about what we this problem doesn't explain, but this is the vertices. Vertices are points. Okay, so here you have 1, 2, 3, and 4 vertices. Edges are these line segments. Okay, so you have 1, 2, 3, 4, 5, and then there's 1 in the back here, 6. And then faces. All right, so if you count, the number of vertices here is 4. The number of edges is, as I said, 6. And the number of faces, how many faces or how many sides do we have? And you can see there are 4 triangles, right? So you have 4, 6, 4 as the number of vertices, edges, and faces. For a cube, you know what a cube looks like. Okay, so a cube sort of looks like this. You have 1, 2, 3, 4. These are the 4 vertices on the top level, and you have the same number on the bottom level, right? So you have 8 vertices. How many edges are there in the cube? You can count. There are 1, 2, 3, 4 here on the top level, 1, 2, 3, 4 on the bottom level, and 1, 2, 3, 4 like columns that connect the bottom level with the top level. So it's 4, 4, and 4. That's 12. And then the number of faces, of course, think of this as a roll as a die. If you have 2 of them, we can call them dice, right? How many faces does a die have? The answer is 6. Okay, so that's the number. Dodecahedron is very hard to draw. I happen to have a lot of practice on this because this is one thing that appeared many times in my graduate school studies. Dodecahedron is basically, it's not exactly a soccer ball. It consists of 12 pentagons, 5-sided polygons connected together. And it sort of looks like this, right? And so if you count the number of vertices, I don't expect you to be able to do this easily. But if you count the vertices, you have 20 vertices. And the number of edges, this is kind of hard to figure this out. But if you count 1, 2, 3, 4, 5, you have 5 edges on each pentagon. And there are 12 of these. But then if you do that, you're counting like this one that is shared by 2 pentagons twice, right? So you have to divide this by 2, right? It turns out to be 30 edges if you count this correctly. Now you have 12 faces because you have 12 pentagons connected to make a dodecahedron. The word dodeca means 12. Okay, that's coming from Latin. In Italy today, dodeci means 12. Okay, so you see the pattern here. Well, numbers are getting bigger. That's one pattern, right? But the point is that in each case, if you add the number of vertices and number of faces, right? So in this case, you have 4, that's 8, right? 8 and 6 add to 14. 20 and 12 add up to 32. So if you have that sum, and if you subtract the number of edges, notice here it's 8 minus 6, 14 minus 12, 32 minus 30. That always turns out to be 2. Okay, so this 2 is independent of the type of solid you have. This number 2 is called the Euler number of the sphere, and so this number will not change. Okay, even if you try a complicated solid like the soccer ball. And if you look at my answers to the notes for section 1.5, you see a picture of a soccer ball, right? In the soccer ball, what you see in the soccer ball is 12 pentagons and 20 hexagons, right? You have 60 vertices and 90 edges. If you have a soccer ball nearby, you can actually count these, and you have 32 faces, right? If you add these, that's 92. 92 minus 90 is still 2. So this number 2 is not going to change as long as you don't do anything strange like drilling a hole in the middle of your solid. And that is independent of the shape, and that pattern is something that you can observe and prove using advanced mathematics. Okay, number 5, this is an example in the book, example 3 in the book. This is another type of math problem, which may not sound like a math problem, but it is. And this is a very clever one. It sounds ridiculously hard, but the answer is ridiculously simple. So simple that you could even call it an elegant proof. Okay, what is that? Pick 5 locations anywhere on the Earth. Okay, now we're assuming that the Earth is spherical. Okay, so pick a sphere and you just pick 5 locations, just pick 5 points anywhere, just anywhere. They don't have to be close to each other, maybe here, whatever. You pick 5 locations on anywhere on the Earth, and we are to prove that there is a hemisphere, and that's half of the Earth, including the boundary circle. Okay, so you have a hemisphere. In this case, I mean, in my picture, the hemisphere is like you have the northern and the southern hemisphere. And when we talk about hemisphere, we assume that it includes the boundary, which is the equator in this case. But anyway, prove that regardless of where those 5 locations are, prove that there is a hemisphere that I can find, which contains at least 4 of these locations. That seems like a really hard thing to do, right? Because we have no idea where the 5 points are. So think about this. How do you even start to prove something like this. You can do some examples. Like if you have, these 5 specific locations, maybe you can do whatever, right? Well, it turns out the problem can be solved very easily if you start thinking in the right way, but the right way is really hard. Okay, so maybe you can think, maybe you can pause this video for a few seconds. I should give you a hint. The hint is that the hemisphere you define is going to include a boundary circle. Okay, so make sure you understand that you can have these points on the boundary of the hemisphere that you are going to find. But your idea is to have 4 points, at least 4 of these points in the hemisphere of your choice. How would you do that? I'm going to pause this, give you some chance to understand. You have to pause your video if you want to solve this. So here's another picture where I just sort of picked random 5 points here. And the temptation may be, try to do a bunch of different locations, like 5. Can you pick 5 locations all in certain, close proximity or very spread apart? But there's a quick way and maybe an easy way, a very elegant way to think about this, right? So you are given 5 points. Okay, you're randomly given 5 points. Yeah. Connect 2 of them. What do you mean? Well, on the Earth, if you are given, let's say, this point and this point, you can connect them with a what we call a great circle, which is like a copy of the equator. Okay, this is called a great circle because this will connect these 2 points with the shortest distance possible. A great circle is basically the circle that goes around the Earth, defining a hemisphere. Okay, dividing the Earth into, or the sphere, into 2 congruent hemispheres, 2 hemispheres of the same size. Okay, so you can always do that. Now this hemisphere, now I have 2 hemispheres, one on this side and one on this side, right? I have connected 2 of these, so 2 of these points, at least 2 of these points are on this great circle that I just defined. How many points do I have altogether? I have 5, right? So I have 3 more points, but these 3 points are either in this side hemisphere or this hemisphere. In this picture, I have this one here and this one here. Okay, so clearly the left hemisphere contains 4 points, because 2 of the points are by definition on my great circle that defines my hemisphere, and 2 more are found on the left hemisphere. One is over here, but remember the question was to find a hemisphere that contains at least 4 of these points. So the idea is this: 2 are already on my hemisphere because they are on the circle I defined. And that would leave 3 more points on the sphere. But I only have 2 spheres and 3 more points left. So one of those spheres must contain at least 2 of the remaining 3 points. And therefore, one of these spheres will contain 2 points not on the great circle and 2 points on the great circle. And this hemisphere contains 4 of my 5 points. That's clever, right? If you ask me this question out of the blue, I probably wouldn't have been able to answer your question. I have a PhD in mathematics, but it's one of those elegant questions where the solution is so simple that you say, I should have thought about this. Thinking outside the box, creativity sometimes is the key to understanding mathematical questions. Okay, you have many other questions in your homework for this section. You don't need to know any formula to do any of these. You may want to go on and do this quiz for section 1.5 first on your copy, and then go online to the Canvas quiz for section 1.5 to do the online quiz. Make sure that you have up to 3 attempts, and only the highest score will remain in your grade book. And remember, you have the answers to all these questions elsewhere in this module. So make sure you get perfect on all of these quizzes, and then you do your homework, which has a lot of great problems as well. Okay, so that will conclude our study of chapter 1. Next time I see you, we will start on chapter 2, percentages. All right, I hope you have a great day, and I will see you later.